Good morning. Welcome to the second lecture in the lecture series of Digital Electronics 18EC302C. In today's lecture, we'll continue with the number system. So we have discussed in the previous class the very popular decimal system, and we have seen some of the important characteristics. Though we know it we are very familiar with that. We have seen some of the characteristics in detail so that we can understand the other number systems used in digital systems. And we have also seen the binary number system, and we have explained the various characteristics of binary number system like the base and the positional values, and how to calculate the value of a given binary number system, binary number. And we have also seen how to count the numbers in binary. In today's lecture, we are going to introduce two more number systems. One is octal number system, another is hexadecimal number system. And so in the first place, we'll be introducing the octal number system. So as the name implies, it's a octal means 8. The meaning is 8. So this number system uses 8 symbols. This number system uses 8 symbols or digits. So starting from 0, you can say the digits are 0, 1, 2, 3, 4, 5, 6, 7. So these 8 digits are used to form any number that represents a given quantity. So since only 8 symbols are used, this number system is a base 8 system. And like all the previous number systems like decimal number system and binary system, the octal system is also a positional value system. That means each position of the number has its value, or the place value of the digit changes with every position. So here the positional values of the various positions in the given octal number are powers of 8. As you can see, as shown here in the slide, you can see there is an octal point. This is very similar to the point that you see decimal numbers as decimal point, and it is also called as a binary point for binary numbers, and similarly this is called as octal point for octal numbers. And to the so this, if you take this as a general number which contains the fractional part also, so there you will find the octal point somewhere in between. And towards the left side of octal point, the position values will be 840, 841, 842, 843, 844, and so on. As you move towards left away from the octal point, and when you move towards right away from the octal point, the position values will be 8 power minus 1, 8 power minus 2, and 8 power minus 3, and so on. So since the octal system is base 8 system, all the position values will be, the various positions will be powers of 8, and there will be the negative powers towards the right of the octal point, and there will be positive powers towards left of octal point. So why basically the octal number system is used? So octal number system is used in digital systems in order to represent the bits in a compact way. So that means when you write a certain, represent certain number in binary, it takes large number of bits compared to any other number system, because the binary contains only 2 digits, 2 bits. So to represent a given number, it takes a lot of large number of bits. And if we have a large number of ones and zeros, it will be very difficult to identify and to be less error prone. So in order to reduce the number of, though the digital system deals with only binary numbers, when it is coming to human, in order to represent and in order to work with the binary bits, they can be written in a shorthand notation by using either octal number system or the numbers in hexadecimal number systems. That's why we'll be going for this octal and hexadecimal number system. So coming to this octal number system, here, for example, we'll take. So we have shown that it has some 8 digits, 0 to 7, and it is a base 8 system, and we say that it's a positional value system where each and every position has a positional value which is a power of 8. And now we can see that we'll take one octal number in specific. And here every octal number should contain only digits from 0 to 7, not more than that. So you cannot have any digit like 8 or 9 or any other digit except only from 0 to 7 digits any octal number should have. So we'll take one such octal number and 76.2. So here also we cannot read it as 76.2 because it is not from our decimal number system. So we have to read it as 76.2. So then what is the value of this 76.2 octal number? So like the previous how we found the value of a decimal number or binary number. Similarly, we will find the value of the octal number. So that is how we'll take the product of the corresponding digit multiplied by its positional value, and finally we'll add sum up all these products to get the actual value of the octal number, or to find its decimal equivalent of the octal number. And here we have shown one example for taking the number octal number as 76.2, and here you can see that decimal point is there, and towards right the decimal point, the first position is contains a digit 2, and its position value is 8 power minus 1, as it is the first position towards the left of decimal point. It's a octal point, right? Octal point. So it is 2 power 2 into 8 power minus 1, and so there are no more bits digits towards right side. So we'll move to the digits on left side of the octal point. The first digit is 6, and its position value is 8 power 0. So we'll multiply 6 with 8 power 0, and the next digit is 7, so and its position value is 8 power 1. So we'll multiply 7 with 8 power 1, and after multiplying or after obtaining all this product, we'll sum up all these. So what we'll get, it is 7 into 8 is 56, and 6 into 8 power 0, 8 power 0 is 1, so it is 6, and 2 into 8 power minus 1, that is 2 by 8, and is 1 by 4 at 0.25. So finally, if we sum up all these, it will comes out as 62.25, and here I can read this as 62.25 because it's decimal equivalent. It's a decimal number. So the value of the octal number 76.2 is 62.25. The decimal equivalent of the octal number 76.2 is 62.25. So I can represent this 62.25, since it is a decimal number. I can use this notation. So this is how. So by to summarize this slide, so we have introduced octal number system, where the number system contains only 8 symbols to represent any quantity, and with these only 8 digits from 0 to 7, you have to represent any number or any quantity. And so since it has only 8 digits, it is called as a base 8 system. And like the previous number systems, it's also a positional value system, but here the positional values will be powers of 8. And how to find out the value of octal number is simply you take the product of each digit value and its corresponding positional value, which is a power of 8. And after taking the products and sum all the products to obtain the value of a given octal number, which is also the decimal equivalent of given octal number. So next we will see in the next slide how to count the numbers in octal system. So you can see in the slide where we have shown how the numbers used, octal numbers are used to count a given quantity, and how the numbers, and we can compare and contrast this with the counting that we usually take up in decimal number system. So in decimal number system, when count starts from 0. So in decimal number system, count starts from 0 and goes up to 9, because we have the 10 digits. It goes up to 9, and after that next count will be 10, and it goes up to 19, and so on. By using 2 digits we can count up to 99, and by 3 digits we can count up to 999, and so on. So that is the story of the decimal number system, where we have 10 digits from 0 to 9. So then, but how about counting in octal number system? So how about counting in octal number system? And you can see that the octal number now, it doesn't have 10 digits, so it has only 8 digits starting from 0 to 7. So by using one digit we can count only 8 numbers, that is from 0 to 7. And after immediately 7, what happens actually? So in one single digit, 7 is the maximum digit. So we have to, in order to make a next count, we have to go for 2 digits, and the 2-digit count will be how it starts actually. A similar way to your decimal counting. So the unit's position becomes a 0, and the next higher position, and here it is called 7th position, becomes 1. It is called units position 7. So it's called units position. So 0 is called units position, and this is called 8th position, not 7th position. Sorry, it is called as 8 position. It is called as 8 position. So for any general number, this is called the units position, and you can see from this position value, this is called 1's position, because 840 is 1, and this is called 841. So this is 8's position, and this is 842. So this is called 64 position, and this is 843, 844 position, and so on. So when we see counting here, you can see when we are using only one digit, the counting takes numbers 0 to 7 that are used to count the first 8 counts, and for the ninth count the units position becomes 0 and the 8th position becomes 1, right? The next count will be 1 1 1 2 1 3 and 1 4 1 5 1 6 and so on, and this goes up to 1 7. So it goes until uh, to the number where the units position reaches the highest digit of the number system. So here it is 7, so it goes up to only 1 7. So we'll not have any 1 8 because 8 is not a part of the octal number system. So 1 7, after 1 7 what happens? Now the 7 units position 7 is the maximum digit, so it has to be changed to 0, and in the 8th position 1 is to be moved, should be changed upwards. So when 1 changes upwards it becomes 2, so the count will be 2 0. So here from here onwards the count increases 2 1 2 2 2 4 3 2 4 2 5 2 6, so up to 2 7. In the similar way, here also 7 is the maximum count in the units position, so it has to change to 0, and the 8th position should be changed upwards, so that is 2 should be changed to 3. So 3037, it goes up to 37, and similar way 40 to 47, and similarly it will go up to 70 to 77. And when it is 7 7, you can see that the units position is the maximum digit, so it should change to 0, and the 8th position is also 7, so it should change to 0. So when both these positions are changed, we'll get a new position for the next count, and in the 64th position we'll get 64th digit in the 64th position, and that bit should be 1. So after 7 7 you will get a new count as 1 0 0. So with one digit you can observe here, you can observe few points here. With one digit we can count 8 different numbers. Something is written mistaken as 10 different. So one digit we can count 8 different numbers from 0 to 7, and with the two digits we can count 64 numbers starting from 0 to 77, which I can say it is 0 to 8 power 2 minus 8 power 2 is 64. We can count from 0 to 77, and with the three digits we can count um, 10 different numbers. So we can count from 0 to 777. So this is how the octal number system works. So here this slide we have shown how to count by using octal numbers. So here you can observe that unit position changes for each count. The units position changes upward with each step in the count. In the 8th position, that is this position changes upwards every 8 steps in the count. So here 1 changes after 8 steps, 1 2 3 4 5 6 7 8. So after 8 steps changes to 2, and here also 1 2 3 4 5 6 7 8. After 8 steps it changes to 3, and so on. And similarly the 16 position changes. 16 position is 1, and this is 8, and so this is 64. So 64 16th position changes after 64 steps in the count, and so on. So this is all about the octal number system. So summarizing the octal number system, So we have shown that the octal numbers is system is a base 8 system. That means it contains only 8 digits from 0 to 7. And like the other previously discussed number system, it is also a position value system. And the position values will be powers of 8. And we have shown how to get the value of to find the decimal equivalent of a octal number system. That is how by multiplying the digit with the corresponding position value and summing up all the production, we get the value of octal number system or its a decimal equivalent. And here we in the slide we have shown how to count the numbers in octal system. So there we have shown that by using one digit you can count from 0 to 7, and by using two digits you can count from 0 to 00 to 717, and by using three digits we can count from 0 to 777 and so on. So with this we will complete the octal system, and next we will go for one more number system used in decimal system. So this is called hexadecimal system. Hexadecimal system. And here you can see that hexadecimal. So the name implies it's a hexadecimal, so 16. So the number system uses a 16 symbol for digits. So here I can say that since it requires 16 symbols, the first 10 symbols will be the 10 digits from 0 to 9, and the next 6 symbols will be the first 6 English capital letters, so A, B, C, D, E, F. Here you can see that the value of the first 6 symbols will be the same, that is 0 to 9, the value will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and for the next 6 symbol the values will be 10, 11, 12, 13, 14, 15. That means the value of A, when you want to calculate the value of number, the value of the A should be given the value 10, and B should be given the value 11, and C 12, and D 13, E 14, and F, the value given for F is 15 when you want to calculate the value of a hexadecimal number. But when we are writing the numbers, we'll be using only these 16 symbols to write any hexadecimal number. So since it has a 16 symbols to represent any quantity, so it is called as a base 16 system. So the symbols will be starting from 0 to F. And like all other previous number systems that we have discussed so far, the hexadecimal system is also a position value system wherein each hexadecimal digit has its own positional value expressed as a power of 16. And here shows how the positional values can be given for hexadecimal number for various positions. And here in the middle you can see we have a point, and this is similar to, this is called as hexadecimal point, which is similar to decimal point or binary point. So decimal point for decimal numbers and binary numbers. So octal point, octal number. So here this can be called as hexadecimal point for any general hexadecimal number. And you can see how the positional values are given. They will be the powers of 16, and towards the right all the powers of 16 powers are negative, starting from -1, -2, -3, -4, and so on. As you move towards right side away from the hexadecimal point, and towards left side we have positive powers for 16. Powers are starting from 16 power 0 for the first position towards left, and for the next position it is 16 power 1, 16 power 2, and 16 power 3, and so on. So here you can see that so we'll be considering some example of a octal number, and similarly we'll find out how to find the value of an octal number, how to obtain its decimal equivalent of a octal number. So here in similar way, how to find out the value of octal number is to simply find out the products of each hexadecimal digit and its corresponding positional value. So we have to take the product of each hexadecimal digit and its corresponding positional value, which is power of 16 here as shown in the above illustration. And finally we have to take the sum of all these products to get the value. And here we have taken an example of hexadecimal number A2.4. So A2.4. So this is a number because we can hexadecimal to write any number in hexadecimal system. We can use any of these 16 digits, 16 symbols. So A is also one of the digit, or one of the symbol of the hexadecimal system. So A2.4 or A2.4 actually represents a hexadecimal number because all the digits of this number are valid digits of your hexadecimal system. So now we'll try to find out the value of this hexadecimal number. So, so this is the decimal hexadecimal point, and here towards the left of hexadecimal point, towards the right of hexadecimal point, you can see the digit is 4. And this digit's positional value is 16 power minus 1, as you can see, 16 power minus 1. And so we'll multiply 4 with its positional value, which is 16 power minus 1, and there are no more digits to the left of to the right of the hexadecimal point. So we'll move towards the left of decimal point. So the first digit towards the left of hexadecimal point is 2, and its positional value is 16 power 0. So position value is 16 power 0. So we'll multiply 2 with 16 power 0. And next we'll move to the next higher digit. It is A. So this is a hexadecimal digit. It is also a hexadecimal digit. So but when we are calculating the value, we have to replace A with its equivalent value. So as we have said previously, the equivalent value for A, hexadecimal digit A, is 10. So when we are calculating, we replace with A with 10, and its positional value is 16 power 1. 16 power 1. So you multiply 10 with 16 power 1. So these are the products, three products that we obtained. So first is 160, and second one is 2 into 16 power 0. It is 16 power 0 is 1, and it is 2. And third product is 4 into 16 power minus 1. So it is 4 by 16. So it's 1 by 4. So 0.25. And sum of all these products, it's a 162. Sorry, it's a 162.25. So 162.25 is the value of the hexadecimal number A2.4. I can say that 162.25 is the decimal equivalent of the hexadecimal number A2.4. So this way we'll find out the value of any hexadecimal number. So simply you can obtain by obtaining the product of each digit its corresponding position value and summing up all the products finally to get its value. So summarizing this slide, and here we have introduced with hexadecimal system. Said that this system has only 16 digits starting from 0 to F, and first 10 digits will be 0 to 9, and the next 6 digits will be the English capital letters A to F. And so 16 symbols are there, so it is called as a base 16 system. And like the previous systems, this is also a position value system, where each position of a number has a particular position value, which will be a power of 16, and the powers of 16 will be -1, -2, -3, -4 as we move towards right, away from the hexadecimal point, and the powers will be 0, 16 power 0, 16 power 1, 16 power 2, 16 power 3, and so on as we move towards left side of hexadecimal point. And how to get the value of any hexadecimal number is a similar procedure, where we will take each digit of the number and multiply with its positional value, which is a power of 16, and sum up all the products to get the value. Next, so I feel that it is clear with how to write numbers, and how to calculate and how to write the positional values, and how to calculate the value of hexadecimal number with this slide. So here, in the next slide, we will see how to count the numbers in hexadecimal system. So here we go, you can observe the table where we have shown the counts. Where we have shown the counts in hexadecimal system, and as the hexadecimal system contains 16 digits, so our first 16 counts can be obtained from the single digits, single symbols, 0, 1, 2, 3 up to F. So 0 to F will give us the first 16 counts. First 16 counts, and you can see, so, and here also we'll see some notation by going to the previous slide. You can see that. So this is called the first place. If there is no decimal point, it's an integer number. If it is integer number, this is called ones position, and you can see that this is called ones position because 16 power 0 is 1, so this is called ones position. And 16 power 1, so this is called 16th position, and this is 16 power 2, so this is called 56th position, and so on. So coming to this hexadecimal counting, you can see that by using a single digit, you can count from 0 to F all the way. So that means we can obtain 16 counts. And if you want to count, if you want to on the next count, the hexadecimal number that gives the next count is 10. Why so? Because so in the units place we have reached the maximum digit, maximum, I can say, symbol, that is F. So the units place must be changed to 0, and the 16th position must be introduced, and it starts with 1. And here also, the, so this will be the 17th count. So 10, 1, 0 gives us. So here you cannot read it as 10 because it's not from decimal system. So here you have to read it as 1, 0. So 1, 0 gives the 17th count, and similarly 1, 1 gives the 18th count, and so on. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and this will continue until its position reaches the maximum highest digit, that is f. So here 1f gives is the number that represents the 30-second count. 30-second count. 0 to f is 16 counts and 1 0 to 1f. So 0 to 1f the 32 counts. So for the 33 count, how we can 1f the next number will be. So as in units position f has reached to its maximum digit, so f should be changed to 0, and 16 position 1 should be changed upward. So when 1 is changed upward, it becomes 2. So 2 0. So the next count is given by the number 2 0, and the count goes from 2 0 to 2f. Similarly 1 0 to 1f, the count the higher counts are given by 2 0 to 2f, and similarly 3 0 to 3f, and so on up to ff. So ff is the maximum count with 2 digits, and here you can see observe that with a single digit you can count 16 numbers starting from 0 to f, and with the 2 digits you can say that you can count from 0 0 to ff, and after ff you can see that the next number which represents the higher count, you can see in units position f is the maximum digit, so replace with 0, and in 16th position should be also maximum digit, so it should be replaced with 0. So we'll get the new higher position, and that should be 1. So it is 1 0 0, and after that the next count will be 1 0 1 0 2. So and up to the by using 3 digits you will get the final count, the maximum number which give the highest count as FFF. So obviously the next count will be 1000, right? So here how we can count by using hexadecimal numbers, and you can observe that a few more things you can observe from this table. The units position changes upwards with each step in the count. With each step into this units position, and here is also this is units position 16 position. So units position changes upward with each count, and you can see that the 16th position changes upward after every 16 steps in the count. So this is 16th position, and this one is 16th position, and this one remains same for 16 counts, and after 16 counts only it changes upwards. So 1 changes to 2, and if 2 with 2, if we completed 16 counts, 2 changes to 3, and so on. And similarly, the next higher position changes upward every 256 counts. That is, this is the next higher position. So this one will change to 2 after 256 counts. So here, how we can count by using how counting happens in the hexadecimal system. So you can observe that it takes some less number of digits, increases some less number of digits to make a particular count when compared with decimal binary number system and octal number system. Hexadecimal number system requires less number of digits to represent a given quantity. So, for example, if the decimal count is, say, for example, 15, so the decimal count 15 can be written by using 2 digits 1 5. But whereas if you want to represent the same count in hexadecimal system, you can represent with only 1 digit, that is f. So f simply it is a single digit, but it represents a value 15, or it represents the count 15. So I can say that the hexadecimal system takes a less number of digits to represent a given quantity amount out of the four number system that we have discussed so far. So most of the times hexadecimal number system is used to represent the binary numbers in a shorthand notation, that is um, compact form. So here these are the characteristics of your hexadecimal number system. So summarizing the hexadecimal number system, you can see that the hexadecimal number system, as the name implies, it has only 16 digits, as the first 10 digits will be your 0 to 9, and the next 10 six symbols are the capital letters A to F. And it is called a base 16 system. As a position value system also, wherein each hexadecimal, each position of the hexadecimal number has a certain position value, which will be a power of 16. And the powers of 16 will be 16 power minus 1, 16 power minus 2, 16 minus 3, minus 4, and so on. And the position values when we move towards right away from the hexadecimal point, and when we move towards left away from the hexadecimal point, the position values will be 16 power 0, 16 power 1, 16 power 2, and so on as we move away from the hexadecimal point. And get the value of how to get the value of a given hexadecimal number means you have to take the product of each digit of the hexadecimal number and its corresponding position value, and after taking the products for all the digits for all the positions, to sum up all the products to obtain the value of your hexadecimal number. So we have also seen how to count how the counting happens with the hexadecimal numbers, where we have seen that first 16 counts um, can be done by only using single digits of hexadecimal system, that is from 0 to F, and next 256 counts requires only two digits, and that is from 0 to FF. We can count the next 256 counts. FF represents 255. When we take the decimal equivalent, so we can count from 0 to 255 by using only two digits in hexadecimal system as 0, 0 to FF. Overall, we can say that the hexadecimal number system takes less number of digits for a given quantity to represent. And this completes the hexadecimal system. And we have so far we have seen the four different number systems, including the very well famous decimal system. So, though this decimal system is not a part of the syllabus actually. So, um, it is the very favorite and very famous and very well used decimal system that the humans are very familiar with. So we have discussed the decimal system in detail and find out some of the characteristics which are the base characteristics of all the remaining number systems. So we have also discussed three more new number systems apart from decimal number system: the binary number system and octal number system and hexadecimal number system. And you can see the basic concepts and the basic characteristics for all these three systems are similar to the decimal system. So the only difference is each number system has different symbols, different symbols. So that is the only difference, and the remaining characteristics are somewhat similar. So you can easily understand if you closely observe, if you can uh, the decimal system and find out the characteristics of decimal system, and you can easily understand the meaning three new systems. And in the next slide, we'll have a comparison of all the number systems, the three number systems, binary system and octal system, hexadecimal system, with the very well-known decimal system. And here are some of the parameters which we can will compare and contrast the number systems. And here the first thing is base. So, so we have seen the base. The base represents actually the distinct digits that are used by a particular number system. So here in decimal system we have it is 10 in binary system, and here also you can see that what are the various distinct digits or symbols used. In decimal system it is from 0 to 9, so they are 10 in number. In binary system the digits or symbols are 0 and 1 only, so they are 2 in number, so base is 2. In octal system the symbols are 0, 1, 2, 3, 4, 5, 6, 7, so they are 8 in number, so base is 8. In hexadecimal system the different distinct symbols that are used to form numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, F capitals. So they are 16 in number, so the base of the hexadecimal system is 16. And coming to the position values, which will be different for all the systems. And you can see that the position values will be powers of the corresponding base of the system. You can see that for a decimal system, the position values will be powers of 10, as the base of the decimal system is 10. And similarly, for binary system, the position values will be mentioned as the powers of 2, as the base of binary system is 2. And similarly, for octal system, the position values will be powers of 8. And for the hexadecimal system, the position values will be powers of 16. And you can see that how many number of relative digits required to represent a given quantity relatively. You can see that so normally I can say that overall I can say that the number system which has highest base requires less number of digits to represent a given quantity. We can see that here among these four systems, the hexadecimal system has the highest base. That means it has highest number of symbols to write any given number. So it takes least number of digits required to represent any quantity. Any quantity. And similarly, out of the four number systems, binary system has the lowest base. That means it has only two digits or symbols to write any number or to represent any quantity. So it takes the highest number of digits to represent any quantity. That means, for example, so if the count is, say, for example, 4, the count is, for example, 4. In hexadecimal system, I can use the digit, only one digit 4 to represent that quantity. And in binary system, the count 4 is represented written by only using 0. We have to use only 0 to 1. So the 4 count can be written as 100. So it takes 3 digits. So to represent the same count, same quantity, the binary system for 4, for example 4, it is taking 3 digits, and hexadecimal system is taking only 1 digit, right? So in a similar way, so the number of digits required depends on the base. So since hexadecimal has highest base, it requires lowest number of digits, least number of digits, and binary system, as it has lowest base out of all the 4, it requires the highest number of digits. In similar way, decimal number system is the second higher base compared to hexadecimal. So it requires somewhat lesser number of digits. And for octal system, the base is 8, which is much greater than the base of the binary. So it requires some lesser number of digits compared to representing the same quantity in binary. So this is somewhat one way of comparing the decimal system as to how many number of digits are required to represent a given quantity. So next we see what is one more parameter for comparison among all the 4 number systems, the application. So where we'll be using all these number systems. So anyway, we'll use all these number system to represent a particular quantity, particular information. So, but we'll be using it various different applications. For example, decimal number system is mostly used by humans, and wherever the humans want to read or write, they'll be representing the quantities in decimal. So, for example, when we are talking to each other, we'll be expressing the quantities in decimal numbers. So that is 10 number of cars, thousands of um, pens, or some 10 number of books, and so on. And but when we want some device to display, the display will be very easy for the human to read if it is displayed by using decimal numbers. So, and also when we want to give inputs for any system, electronic system, we want to prefer to input the quantity by using decimal numbers. So we'll not be preferring. So whenever there is a human involved, we'll be preferring decimal system. And whenever there is machine involved, whenever there is a machine involved, in particularly as a digital systems, we'll be using binary system or octal system or hexadecimal systems to represent any quantity or any number, because binary system, and out of this binary system is the preferred one for the digital circuits, as it will be very easy to produce only two different work with two different distinct voltage levels. So binary system is the most preferred one for us digital circuits, as it is very easy to implement the circuits inside. But the binary system is easy for the machine and to make up the circuits, but it is very hard for the humans to interpret and use. So to interpret the binary system in a compact way, we'll be using octal system and hexadecimal system. These two systems are used to represent the binary numbers in a shorthand representation. So this how we can represent a very large binary number as a very small octal number are just very short, in shorthand notation by using hexadecimal system that we can see. Then we'll see the conversion from how to convert when we see the conversion of binary to binary number to octal number or binary to hexadecimal number. So there we'll identify how we can represent or how we can see how we can represent a very long or large binary number as a shorthand notation by using octal system or hexadecimal system. So overall, we should be familiar with all these four systems because we are the humans will be designing the digital circuits. Though the digital circuit is working with the binary, so it should be represented and interpreted and understood by humans. So we have to be familiar with all these four number systems, and we should be thorough with all these number systems and how to represent and how to make count in different number systems and how to find out the value of a number in given number system, and finally first how to write the numbers by using various number systems, or how to represent a given quantity by using various number systems. So all these will be useful to work efficiently with the digital circuits that we are going to learn in the incoming chapters. So with this I conclude the number system and the comparison of the number systems, and we'll explore the basics of other uh, concepts of digital circuits in the coming classes. Thank you.